Hello everybody, this is Mr. Arocena. On today's lesson, we'll be talking about enthalpy changes in reactions. We didn't talk about enthalpy too much in Chem 11, other than there were two types of reactions, endothermic and exothermic, and we kind of left it at that. Today we're going to go over what exactly we mean by endothermic and exothermic from a very mathematical standpoint. Alright, so let's get started. Alright, so whenever a chemical bond is created between two atoms, it requires a certain amount of bond energy. Interestingly enough, when chemical bonds are created, they release energy. This leads to systems which have less energy, and because they have less energy, they are more stable. So, sort of think of it as, if I go back to my kindergartner example from before, if I remove kindergartners from a room, the room acts more stable because there's just less energy in the room. So chemical bonds are kind of the same way. If you make chemical bonds, they release energy so that the bond at the end of the day has less energy, and therefore the system is stable. By contrast, breaking a chemical bond requires energy, and in order to do that, you have to give the system more energy. When you give the system more energy, that leads to states, or leads the system to become less stable. Maybe like throwing more kindergartners into a classroom. Very unstable, and eventually something will break. Bond energy, by definition, is simply the amount of energy that's needed to either make or break a chemical bond. But this is strictly between two atoms. Okay. So if I were to illustrate this, bond energy exists between two atoms. So if this was two atoms like this, this would have some bond energy. Right? And it's only between these two atoms. If you have a compound composed of multiple bonds, like some of the large organic molecules we dealt with in Chem 11, then the bond energies would be unique to each specific bond. All have bond energy, some bond energy. Each of those bonds has their own bond energy, and in order to break that chemical bond, you need to give it some energy to break the bond, and then when the bond gets broken, they will release energy. So we have to supply energy. Energy needs to go into the bond, and then when things get recreated, this join together, join together, they will release energy, achieve a state that is more stable with less energy. Okay. Alright, so that's what bond energy is. And bond energy, the amount of energy required to break a bond is the same as the amount of energy required to make the bond. Okay. So in this this first example, breaking the bond between the chlorine atoms in a chlorine molecule requires energy. The amount of energy required to make the bond is exactly the same. 243 kilojoules required to make the bond. Right. So the net result is then that if I want to break a bond, I have to supply some energy make the bond have to supply same energy. That's only between two atoms. So how then do we get endothermic and exothermic reactions? Well, that depends on the energy of the entire system as a whole, right? Because the bond energy is specific to pairs of atoms, but most chemical reactions deal with a lot more than that. So the system energy will determine whether a reaction is endothermic or exothermic. And as the name suggests, system energy is simply defined as all the particles involved in the reaction. So if you take all the energy of all the particles involved in the reaction, that is going to be your system energy. System energy, all the particles involved in the reaction. And the system energy takes into account both the potential energy of the system as well as the kinetic energy of the system. If you remember, for those of you who took Physics 11, particles contain many different forms of energy. There were, I think, three different forms of kinetic energy, and then potential energy. Potential energy is simply defined as all the attractive and repulsive forces in the particles. So, for example, these would be usually these are defined as the positive and negative charges will cause attractive and repulsive forces. So the protons in the atoms and the electrons swirling around the protons, they will cause attractive and repulsive forces between the particles. And this potential energy then leads into the bond energy. So the potential energy is heavily dependent on the bond energies of all the bonds present. So if you have a lot of bonds, the potential energy tends to be a lot higher. Less bonds, potential energy tends to be a lot smaller, simply because there's less particles involved, so less positive and negative charges are involved. The kinetic energy is just simply due to the movement of the particles. So if the particles are moving really fast, they will have a lot of kinetic energy. If they're vibrating very fast, they'll have a lot of kinetic energy. If they're spinning, they'll have a lot of kinetic energy. So the system energy is all of these energies combined. Okay. Now, how the system energy changes will determine whether the reaction is endothermic or exothermic, and we call this the reaction heat, which is not always the best way to describe this, but it's the one that we use the most. So this enthalpy is really just a change, or I guess a measure of the energy of the system. Here we'll define it as the total kinetic and potential energy in a system at constant pressure. And we can sort of say then that in any kind of chemical reaction, the products, so that's this here, the product heat, so this is product energy, and this would be my reactant energy. This quantity here, this will be change in energy. So we'll call energy enthalpy in this case, change in energy. So I'll probably be referring to enthalpy and energy kind of interchangeably, so just keep that in mind, that enthalpy really just total energy. And what we look for in a chemical reaction is this quantity here. We observe this. Generally don't observe or don't measure the product energy and the reactant energy. These are actually, so this here and this here, actually quite difficult to measure, but this quantity here is relatively easy to measure given a chemical reaction. So in a chemical reaction, if the change in energy is negative, then the reaction is exothermic. You sort of think of it as the reaction loses energy to its surroundings. If delta H is positive, the reaction is endothermic, which translates to reaction gaining energy from the environment. And like I mentioned, generally we don't really care too much about the energy of the products or reactants because that's not entirely useful. We just tend to find the change in enthalpy so that we know whether it is exothermic or whether the reaction is endothermic, and by extension, how much energy is either released or how much energy is absorbed. Okay. So here's an example. Here's the following reaction. This is the creation of, this is nitrogen gas and oxygen gas combining to form okay. This particular reaction is endothermic, and it will absorb 164 kilojoules of energy. So we can show this in an enthalpy diagram. So that's what this here is. So this is an and you can show that the reactants, for an endothermic reaction, the reactant energy, here's the H products, is lower than the product energy. And then the delta H will be this quantity here, delta H here. So delta H in this case is greater than 0, so greater than 0. Now what you can see here is that in an endothermic reaction, the H products, the product energy is greater than the reactant energy, because the products, you can think of it as the products have absorbed energy. So as a whole, the product side is at a higher energy state than the reactant side. Okay. Now, by contrast, an exothermic reaction like the one in this example. So here, this is hydrogen gas combining with chlorine gas to make hydrogen chloride. This particular reaction is exothermic, and the reaction or the enthalpy diagram will look different. Okay. So where the endothermic reaction had the products at a higher energy state than the reactants, the exothermic reaction will have the products at a lower state compared to the reactants. So here's H reactants, here's products, and delta H ends up being negative in this case. Okay. H is less than 0 or negative for exothermic. And H products, so the energy in the products is less than the energy in the reactants. And if you think of it this way, in an exothermic reaction, the reaction releases energy to the environment, so the end result is that the products have less energy than the reactants that created them in the first place. Okay. Yeah, so that's what this diagram is. These are, again, just an energy diagram to show how the energy between the reactants and the products changes for both an exothermic reaction in this case and then the endothermic reaction in the previous case. Alright, so let's go through a quick example of how to draw one of these diagrams. Okay. So consider this reaction. It has a enthalpy change of plus 287 kilojoules. Draw the reaction energy diagram. Energy on the y-axis, time on the x-axis. So here we go. Right, so here it shows we have a positive 287 kilojoules. Delta H is positive, delta 0. This is going to be an endothermic reaction. And in an endothermic reaction, Oops, not a delta. In an again. In endothermic reaction, H of the products greater than the H reactants. So the products will absorb some energy, so they will be somewhere up here. Products. Reactants will be somewhere down here. That, and they will gain some energy to go up that way. And this height here will be 287 kilojoules. Well, that's how we should view this information, is when we get a certain type of reaction, whether endothermic or exothermic, we just see, okay, how does the energy differ from the reactants, so energy from the reactants, how does that differ compared to the energy in the products? And what that will tell us is whether the reaction is endothermic or exothermic, and what kind of delta H change we will end up seeing. Alright, there you go. So that's what enthalpy is. Enthalpy is just, up this, enthalpy, simply just the energy of the system. Alright, if you guys have any questions, you know how to contact me. And if you don't want to contact me that way, come find me in the morning or later this week and we can talk about it. Alright, your assignment for today then is as follows. Yeah. Guys, later.